Hi guys. Um, in this video, we'll attempt to understand the transformer architecture. So, if you have just seen this architecture and you're eager to learn its components, um, I hope I will do the right job to you know to make you understand the this fascinating architecture. Um, you know. In this video, I'll try to alternate between the why and the how. First, I'll try to you know I'll try to explain why this architecture is amazing, and after we'll proceed to the hows. And I think by the end of the video, you'll be really confident of your knowledge on this. Um, so before jumping into this architecture, um, we'll kind of you know ask some questions. So what's an LLM? Because this transformer results in a chatbot. I know that you've used ChatGPT, that's for sure. But when you enter ChatGPT, what's the first thing you see? You see a bar where you enter a text. That's that's the most important part in ChatGPT. Um, and that's why what we call query. A query is a text that we send to the model, and that model gives us some babbling which resembles to that text. And that's the main thing about this transformer architecture. Two important parts in models, in AI models, is training, where we bring that model into life. Model is first only the skeleton. This is only a skeleton, but when we feed it data, its mitosis procedure. It makes its flesh and its bones and whatever, and by the end, it's a fully fledged LLM composed of what you've trained it on. If I trained a model on I don't know, on Shakespeare text, it would generate me Shakespeare-like text. If I don't know, you get the idea. The goal of this architecture is to compress data into an intelligent, a higher dimensional space. And you know, intelligence, after all, is nothing but compression. We only compress. The goal is to compress data. But when you decompress, or when you do the inference part, the inference is the after the model is is mature, we inference it. We give it input, and it gives us output. And that's what we do with ChatGPT and many LLMs in the industry. So first, it would be really silly to think that we give raw text into the model. You know, models, they don't understand what text is. They only deal with numbers. And so the first thing we think about doing when we want to inference or train text, the model on text, first we tokenize this text. The first part is called tokenization, where we take text, which is blah blah, blah blah. We turn it into a set of vectors, 32, 32, for example, where blah is 32. And the tokenization dictionary, the dictionary is a dictionary of keys and values, where somewhere in this dictionary of blah is 32. There are many tokenization dictionaries. Most important and most famous one is Word2Vec. It's developed by Stanford or Google, I don't know. And the goal is to transform this text into an understandable form by the model. And so here we get we do not only transform it into floats and integers, but we transform it into a higher dimensional space. Higher dimensional space you could think of it as blah, meaning 32, and this 32 points to a really huge vector with the size of the model. And the goal of this is to map our text into higher dimensional data, into a vector space. And a vector space resembles to something like this, where we have where we have many dimensions, and text is mapped, where each word is put in the perfect place. And it's not really we could think of it in a different way. It's the distances between words. The distances are in the perfect place. Each word isn't too far nor too apart from the other word, and that's what we uh, want to achieve in a higher view um, through this transformer architecture. Yeah, you could think of it. A matrix is nothing but a dimension, a higher dimension. To a lot of dimensions. So here, when we tokenize data, we we transform text into a higher dimension, into something like this. And now, uh, this is nothing but a matrix, and a model, it could understand that. The second thing we try to achieve is positional encoding. As we'll see later in this video, transformers they don't tackle local receptivity. Um, I don't know if you, for example, for CNNs, we have kernel windows where each pixel is the closeness of pixels is understood by the model. But here, this only in this part, it doesn't really handle the local problem. As we know, distances of tokens is really important, and that's why we'll incorporate positional encoding, and we'll just add tokens. We'll add to them the positional encoding. As easy as it sounds, positional encodings are nothing but sinusoidal functions that kind of map, kind of give meaning of the closeness of the tokens. Um, we'll try to get into that later. There are many more interesting positional encoding techniques. This one is, the standard thing, but lately there have been many advancements in this subject. Uh, there's been a rotary positional encoding. Rotary, you can look that up. I'll try to make a video later on that. Rotary positional encoding. It's really interesting, and it outperforms this symbol function. So after we tokenized our text and gave it positional meaning, now we're gonna get into the heavy stuff. And one of the most important mechanisms in transformer architecture is the attention mechanism. So after we've got the input sequence, the token, which is of dimension sequence d model. Now we're gonna create 3 copies of this matrix. One, we're gonna call it Q, which is query. One called keys, and V, which is value. So the goal of this query is what I want, key is what I am, and value is what I have. And the goal is to start communicating with other. Each token communicates with all of other tokens, and we train this model to obtain perfect scoring of the relationship of each token. That's the basic thing. And after we have make a copy of these tokens and name it Q, K, and V, we'll multiply these. These have this dimension, and here we'll construct learnable parameters. Learnable parameters are parameters that will go through backpropagation and will try to decrease the loss of the model via gradient descent, and this is a matrix. We'll try to modify the parameters of the matrix to minimize the loss of the model. The loss of the model is the reconstruction of the text we gave it, or the prediction of the next token via autoregressive. Yeah, yeah. So here we have WQ, WK, and WV. So when we the size of these matrices are the model, the model. And the goal of this, why did we choose this shape is so when the matrix multiplication is done, we'll end up with a matrix of size sequence D model. We'll preserve the dimensionality. And this dimension Q, I'll call it Q prime, K prime, and V prime. And this is where the we'll get into the an interesting part, where we'll divide these three matrices by H, where H is the number of heads, because as we've seen here, we have multi-head attention. Multi-head attention. We kind of divide the D model, the dimension of the model, into 4 parts. And the goal of that is to parallelize computation and end up with the optimal attention scores. So here we'll end up with multiple heads, typically H heads, and the sum of all of this is equal to D model, the sum of the columns. Same here, same stuff. Yeah, same. Where each part is of size sequence D model over H. And after dividing into H heads, for each head we'll, not for each head, but we'll apply the attention mechanism, which is the crux of the transformer architecture. So the attention mechanism is basically attention of Q, K, and V is equal to softmax of Q, K over D model times V. And softmax is a function, it's this function basically. It's a of x over xi, let's see, it's xi over sum of xi, let's say xk, I don't know, xk of I from 1 to n. So this basically gives us a probability of x, probability of x, and the sum of the probabilities of x's is equal to 1. That's the goal here. And this, the product between the query and the key. The query is what I want, and the key is what I have. The product, it gives us the, is it the real thing that you want? This is the probability that you get by this function. And for each head, we'll apply this operation. So we'll get head prime, H heads, and we'll concatenate these heads into one small matrix. Let's do a simple dimension computation here. So we have Q, T, and V. Their shape is sequence D model. So Q transpose K is equal to sequence, you know, because it's sequence model, you know, because something of the shape AB times BA, the matrix of the shape of the matrix product of these two is equal to AA. So that's what we get here. And QT times V, QTK, sorry, times V is of the shape sequence D model. So we preserve our initial shape, and we've calculated the probability of each interaction of each token, and surely the elements with higher probabilities are the desired ones. So yeah. As you can see here in the softmax function, we divided by D model. Sorry, let's go into another page. You know, the attention is softmax of Q transpose K over D model times V. Well, as you can see here, we divided by D model. D model is nothing but the Euclidean distance of Q transpose K. And why do we do that? Why do we normalize? We normalize because we don't want exploding gradients. What do you mean by exploding gradients? In a matrix where we have really big numbers, real big floats, calculating the gradient descent will result in a very, very huge derivative, and it's gonna cause us real big problems. So when we divide by D model, this result it will result in a matrix of D model with fairly small numbers. So the gradient descent will be kind of, it will run smoothly and without any problems. And there's a relationship between normalizing and smoothing. Smoothing the loss function. The loss function is nothing but a convex plane. It's not in 2D. It's more, but it's not as smooth as this. You could find some hills, some small hills, but the goal is to reach the minimum value of the loss function, where the derivative of the loss is equal to 0. So this loss is made of the loss function is made of the values of the values of the model, the D model matrix and other MLPs and whatever. So it's the params of the whole model, and it's a really complex shape, and we try to go down the hill steep, the hill to reach the minimum variable. And the gradient descent, just to give you an idea, gradient descent, we for every single model we kind of xi is equal to xi minus loss over xi. So a loss in every single model in AI, we have two important things, one of the most important things is the loss function. You need to create a suitable loss function. So when at first we set these initial variables in the model randomly, and after each step, after we calculate and stuff, we backpropagate. For every single element of the model, we subtract the loss over xi, and I forgot to add a beta, where beta is a grade, I forgot the name. A learning rate, yeah. Beta is a learning rate, and it sits. It depends on the algorithm, on the optimization algorithm, but it's really small. It depends on how many times we subtract from this parameter, but it's overall it's in the orders of 10 to the power of -3, and yeah. So we explained why we divided by D model here, and why we multiply by V, and So in the end, we get something of the shape sequence D model, and we're here. We're here. We're only here. Um, so as you can see, this simple line here. The goal is to when we've calculated the sorry, when we've calculated the the final matrix of size, when we concatenated all the heads and stuff, we get a matrix of size D model. Sorry, sequence D model, and we have the initial input tokens. They have sequence D model. What we try to do here is to add. Let's call this x prime and this x. The goal is to add x prime equals to x prime plus x. Yeah, or let's call this f of x, because this is a function basically, and where are we? Yeah, x plus f of x, and this is the goal of this is to these are called skip connections, and you'll see them everywhere you go in AI architectures. Skip connections, and the goal is to, as we said earlier, we have a loss function, and the loss function is made of the input tokens and whatnot. Holy shit. The goal of adding, the original input to the transformed input is, it's not really transformed, but it's another thing. It's f of x is the relationship of every token to the other token. It's kind of we applied an aggressive transformation on the input. So we've kind of lost the original, the original meaning of the input data. That's why we incorporate this skip connection to preserve the gradient, properties of the model. To not, if we don't add that, we'll have the vanishing gradient problem, which is something you don't want to get into. So yeah. And after we add after we add the original input to the transformation, we apply the norm, the layer norm. Although, as I wrote here, we could add RMS norm instead of layer norm. It's computationally efficient. It doesn't really require as much computation as layer norm. But in the original paper, they incorporated layer norm. So, yeah. And the goal of normalization is to, as we said, we don't want our data to be really big, or or close to zero. That's not something we want. The goal is to have input data in a good range, so that the training process will run smoothly. This part here, we've only covered the multi-head attention, but in the case of masked multi-head attention, we add one small thing. Masked means that every token doesn't get to see its its children. No, not its children. It's its following tokens. For example, here when we multiply this k transpose k, we get a matrix of size sequence, and the trick here is to transform this qt into a triangular matrix, where this part we leave it intact, but this part we fill it with minus infinity, and the goal here is to harness the property of the exponential. That exponential minus infinity tends to zero. So that when we apply this softmax to this function, every single token here it gets zero, and we only end up with probability of this. We get probability of this, and the probability for example of this one is based on itself and on its past, but not on its future. So the goal here is to condition every token on its past only, because it's kind of, there's no meaning if we condition a token on its future. The future is up to us. We want to predict the future, but the past is a data that we could take for granted to generate more accurate tokens in the future. That's why we don't incorporate future tokens here. It doesn't mean anything, you know. In French or English, we write from left to right. You know, uh, I can't see why we would incorporate, tokens on the right to to condition them on to condition tokens on other tokens on the right. It doesn't have any meaning. So that's why. Moving on. We've explained the layer norm, why we did that, add norm. It's perfect. Um, in this video, I'll try to cover only the decoder part, but on the end, I'll tell you how to add this and, what would be the meaning. But we'll focus on this part. This part is really crucial, is the crucial one. This one is responsible for ChatGPT and whatnot. This could help in the text translation and other stuff, as I said. So in the case of a decoder, we won't need this part, because this part is responsible for when we compute the relationship of each token and you know the input token, each token and its past tokens. We get that. Now we want to compare our current tokens with the encoder tokens, and basically it's the same thing here. We don't apply the mask, but we replace our I think so in this part we only we do the same computations here as we did here. We do the same here. We'll go into depth later on the MLPs, but when we compute all this, we send only the keys and values, and it's quite logical because we only want what I am and what I have, and here what I want. So there's an attention of both. We in the attention function we calculate a dot product of q and k. So it's this query here and the keys here, and then we add the value. We dot product with the value, and the same add a norm and the MLPs. So it's I hope I gave a good explanation on this. Yeah, let's jump into the multi-layer perceptron and try to understand why and how. So now that we have we've got the add we've normalized and added skip conditions and all of that. We move to the MLP or feed forward. This model takes a matrix of shape sequence D model. We put it into this black box, and we get a matrix of shape sequence vocab size. And vocab size basically is the set of elements, of possible elements that we could get, that this model could generate. And for us, it's text. It could be alphabets, I don't know, and special keywords and whatnot. If you don't know, an MLP is a multi-layer perceptron. A multi-layer perceptron is a neural network. The input, it's of the shape. This is only a miniature, but you could extrapolate on real cases. So yeah, basically it's all that. The basic property of a this perceptron, you know, this is a revolutionary architecture. The input is of size here sequence times the model, if I'm not mistaken, and here it's of sequence times vocab size. Each neuron takes a value. So here what we've done is we flattened. Imagine we have a matrix of this size. We have, I'll give you a concrete example. We have here 1, 2, 3, 4, 5, 6, 7, 8, and 9. Well, what we do is we take this and transform it into 1, 2, 3, 4, 5, 6, 7. We flatten. We put it in here, and this we put it in here. We flatten so that it kind of fits the model. It's like one line, and then we pluck it into the model. The model starts, pushing. Every single neuron here is connected to the next layer's neurons, and same for here. And this is what we call the hidden layer, hidden layers. Here the size is 3. We have 3 hidden layers, and the more we add, the more we go deep, the more the more the model understands the complex meanings in the data. And in the end, we add a model with the with this output. So as you can see, the output is flattened, but we could transform it into the matrix that we want. So after the attention mechanism and all of that, we still feed this data into an MLP. An MLP it understands the complex. It further understands the context of the data, and it gives us more information and more understanding to the model. Each layer here we incorporate non-linear activations. Most used ones is ReLU. ReLU is max of 0 and x. So it only takes positive values, and if it ever sees negative value, it puts it to 0. But this problem with negative values is quite a problem, because if the value is 0 here, for example, this is a dead neuron. This is 0. This gets deactivated. If you had 1 or 2, I don't know, if you have a few dozens in a really huge neural network, it's not a problem. But when we have many dead neurons, the model is it's good for nothing. It serves for nothing. That's why there are some variants of this ReLU. I know something called LU. It's max 0.1 of x and x, something like that. At least here we don't set it to 0, and we preserve our valuable gradients. Yeah. And this, at first it's the model parameters are set randomly, and then we start doing gradient descent, and the parameters are fixed in a way that maximizes minimizes the loss, and that's what we want. So when we get a final matrix of size, sequence, vocab size, as you can see here, we add norm with the same thing we did here to preserve our gradients, and yeah. But since this add norm, since we add here the skip connection, I think the output, what I've done here is the totality of this, is I've did everything here. but I skipped this one. So um, suppose this one is the place where we do add a norm. Uh, the shape of this is sequence D model. This is the one before the last layer. The last layer is this linear layer, and here in this place we apply softmax on each element, so we get probabilities, and here we add the we add the matrix that we've got here. This one we wouldn't use it, so straight to our MLP in this place, add norm, then forward to this linear feed forward where we applied softmax, and in softmax we get probabilities, and that's what we want. So when we get probabilities, we get probabilities of so it's sequence vocab size. Sequence vocab size. And what we get is imagine we vocab size, vocab size A, B, C, D's, whatnot, and we select the column with the highest probability. What does that mean? What does it mean to have the highest probability? Imagine, sorry, kind of zoned out for a while. Imagine we fed into this model. It's trained and all, and we we said, I don't know, Trump was born in, and we feed it that. And imagine that our model is trained on, scraped data. It's data from the internet. It's sorry. Imagine that the model is trained on Wikipedia text, and all of the text in the world. So if we feed it that, if we apply all the transformations and all that stuff, we would get here a token which is 100. Imagine if the vocab size only had 1 to 9s, it wasn't as complicated. We would get 1. It would give us 1. And then we would take that 1, we would put it in the input here, and we would feed it once again into our transformer, and we would get I don't know, a 9, probably a 9. We would do that again. It's auto-regressive. This property is called auto-regressive sampling. Is it sampling? Yeah, I think it's sampling. And we would get probably a 4. I don't know. It's not 4. It would be a 6 maybe, and I don't know, another value. And yeah, that's what we would get. But this is only a raw transformer. There are many other techniques that kind of that we would add if we want to this model to be more interactive, and and many stuff we would discuss later in other videos. As we said in the beginning of the video, LLMs are nothing but knowledge compressors. They only compress what they see, and there has been a problem with a chatbot called Tyler. There has been a problem with a Twitter chatbot that they developed when first Transformer emerged. They trained it on Twitter data, and when they kind of deployed it into production, they noticed that this chatbot was kind of racist. It was replying using racist words and stuff. So generally, when we train LLMs on internet data, well, internet data is filled with garbage. It's filled with bad words and stuff. So what we do is we kind of align it. We try to align it to our human values. We uh, we try to make it, more friendlier, stuff. Good moral values. Depends on your needs, but you could align it to whatever you want. And there are techniques that I'll leave you if you want to search them up. It's called DPO. This one is state of the art. It's really interesting. But there's also RLHF. It's called reinforcement learning from human feedback. This one I don't know what it stands for, but this one is way better. And this one, you know, you need a lot of computation to apply it. Whether this is way easier, and it's computationally efficient. So I hope you know I kind of took you on a walk in this transformer architecture, and you now understand you know the why and the how of this transformer. Um, there's a comment section below. Don't forget to add any suggestions, and um, if you want me to talk on other subjects, I'll be happy to. Um, so yeah, I'll leave you on this section. Have a good day, and see you next time.